Hi, this is a model I've made I'd like to describe to you. That's the purpose of the video, is just to demonstrate this, show that it works. What it is a method of transmitting power to an output, and it does it with positive gear engagement. There's no friction material, no clutch pads, there's no hydraulic oil such as what would be in a torque converter. It's all positive gear engagement. And what I'll do is I'll go through the components, I'll demonstrate the model, and then I'll switch over into this little sketch that I made down here, and go through some of the math on it as far as why does it actually work at all. And um, that way I can show you all the components that are obscured up here. It's kind of difficult to show some of these. And then I'll go into just a few examples of different areas of mechanical engineering discipline where it could be useful. So the model here is got a little motor down here, just a gear motor that runs up to a shaft, drives this crankshaft. The another part is the sun gear is a 2-inch sun gear. It's connected to a plate, and then that plate is connected to a ring gear. So that's one unit right here. And then I have this planet gear set. Well, the planet gear set is 1.5 inch outer planet gear. Below it on the same shaft is a 1/2 inch gear, reducer gear, and it's engaged in an inner planet gear that's down below, and that is engaged into the sun gear. You can just see it down here. There's a bracket that connects the two of the planet gear assemblies together, keeps them steady with each other, and that bracket has an extension that comes out here to a lever, this lever right here, and that's my control. If I push on the control now, I'm actually putting output out. Now the only thing I'm doing when I push on this is I'm making this axle go backwards. I'm putting a force on it, a backwards force, and the inner planet gear, I'm putting a force on it in the opposite direction. It's just a leverage system that works with the axle that's connected to the crankshaft. It's very simple. Simple is good. Over here I have a load. This load is connected to a spring, and it's just a friction pad that's pushing against this plate and the ring gear. If I activate some power to come out to it, and for some reason it increases, well, all I have to do is just increase the control signal, and in that way I can vary the amount of torque that's being fed out by applying more pressure on these two gears. And that essentially is it. See, now I've got output power, and now I'm in neutral. So how does all this work? Well, down here I've omitted the little lever because that would just muddle the drawing, and I've replaced it with this arrow just to indicate that I'm pushing on this bracket. So here's my axle from the crankshaft. It's in the center. Then I have these other two axles connected to the planet gears. And as long as I'm not pushing on this lever, well, then the crankshaft just simply moves the planet gear assembly around in the annular space. If I apply pressure here, well, now I'm going to apply a force on this axle in this direction and a force on this axle in this direction. So as far as the math is concerned, let's just say for an example that I have a load out here that's attached to the output that requires me to put 2 pounds of pressure on this axle right here. Well, if I need that and I apply a pressure here, then I'll have, let's just say I produce 5 pounds, we'll call it minus 5 pounds of pressure in this direction, plus 5 pounds of pressure in this direction. Well, this is a 3-to-1 gear ratio here, and this is 1-to-1, and I had 2 pounds of pressure here already from the crankshaft. If I sum all the pressures up, what I'll have is a -4 here instead of -5, and over here I'll have +6. -4 right here with this ratio makes -3 here on the teeth of this planet gear where it's engaged. -1 over here. Well, over here, remember I had 6 pounds, so I'm going to have 3 pounds of pressure here on that inner planet gear and 3 pounds over here. If I got 3 pounds positive here and 3 pounds negative here, they're balanced. They're not going to rotate anymore. I also have that 3 pounds over here, remember? Well, it's connected to the sun gear, which comes over here and is attached to the ring gear. And that means I have 1 pound of force on the ring gear where it's engaged in this outer planet gear, which was producing -1 pound. So they're balanced. Well, there's a balance here, balance here, balance here. These gears are no longer going to turn. And the only thing I'm left with is the 2 pounds that I applied here from the crankshaft. Now in the real world, you'd probably multiply those pressures by either 10 or 100 or whatever's necessary. But for the model, we're just working with small numbers. You'd also probably change this bracket where it would extend on up here and connect to some sort of an actuator that would also engage a whole multitude of other planet gear sets, because then you get to multiply the total amount of torque that you're going to be able to deliver to some device for any given size planetary gear system. So that's how it does it. Now, let's just say that you actually wanted to do something with this where it was a soft start condition. Well, in that case, you'd use centripetal force. You might actually have a lever like this with a weight on it. And if this is an internal combustion engine that's running this, well, then it gets to get started and come up to idle speed at least before this generates enough pressure to start delivering power to a load. You could also do the same thing with an electric motor. If you're working with HVAC systems and you want that motor to operate a large air handler, then you'd have a soft start condition. That would enable you to possibly redesign your entrance wiring, because it no longer has to sustain a huge surge current to that motor if the motor is not instantly loaded the moment you start it. So there would be some cost savings there. In the discussion with an internal combustion engine, maybe you'd want to optimize that brake-specific fuel consumption curve on that engine by modifying the intake and exhaust plenums, the valve timing, the injection timing. If it's gasoline, maybe spark advance as well. That would let you make that engine run at a very efficient RPM setting, and as long as it's designed so that it's above anything that you would ever expect to run out here, then you can use this by servoing it with a tachometer and adjusting the input control force to proportion out however many RPMs you need from 0 up to the engine speed. So that might be an advantage there. Maybe you work in with windmills. There's a generator up in the side one of those windmills that needs to run at a specific RPM setting in order to be synchronized with the electrical grid. I think it's 1800 RPMs is kind of a normal. Well, if you have lots of wind gusts and irregularities in the wind that's feeding those propellers, you can use a servo in order to make sure that the output from a device like this stays at a constant 1800 RPMs. How about locomotives for another example? If you currently use a generator to vary that output by converting mechanical from a diesel motor into electrical and then into switchgear to condition it to run traction motors before you finally get it to go back to mechanical energy to run those traction wheels, well, there's some inefficiencies there. This would allow you to have that disconnect where you just apply as much torque as needed to nudge those cargo carrying cars together when you're coupling them in the train yard, and then once you're out on the main track, you just apply the full force through this out to the wheels from the engine, and you can go several hundred miles with a complete mechanical to mechanical connection. What about bulldozers and skid steer and zero-turn mowers? Well, this would allow you to connect one of these to one side of that machine and a second one to the other side. You might go ahead and make it a tandem setup where one runs clockwise and the other runs counterclockwise. Now you can control either a forward or neutral, or activate the reverse system, and you'll have full control over that big machine as long as you do that on both sides. In the automotive industry, you could do the same thing where you have one of these running one side of the car and the other runs the other wheel on the other side of the car. If you did that, you could have a algorithm where when the driver is going around a curve at speed, you can actually proportion a significant amount of the torque to the outboard wheel versus the inboard wheel and have some active steering for better handling. You could also use this for a multiple clutch system in any transmission where it just engages different speed ranges instead of using clutch packs and brake bands and things like that. You might use it in a reverse operation where you connect the output to the frame of a vehicle and the input to an axle that's connected to one of the wheels. Now you're just transferring torque out of the wheel to the frame of the vehicle and creating essentially a brake. That might allow you to remove the rotor and the caliper that are out there on the wheel assembly. That would make the wheel assembly much lighter for better handling. You might be able to redesign the suspension system and the steering controls as well, since the rotor's not out there. In addition, that heat buildup on the rotor isn't right next to the rubber tire and the wheel bearing. So those are a few examples of different things that could be done with this. I'm sure there's many more. If you have any other ideas with your expertise in different modalities, you could share those with your friends and colleagues, and who knows, if enough people come up with enough ideas and spread the ideas around, we might actually be able to change the world for the better. At least we can make some of the machines that we all work with work better and more efficiently. So I want to thank you for your time and have a good day.